All right, so you're into philosophy, and infinity is kind of your jam. Well, strap in, because today we're taking a deep dive into supertasks.
Supertasks.
Yeah, they're these, well, theoretical tasks with a twist. They have infinitely many steps, but you got to do them all in like a finite amount of time.
Oh, that's a fun one. Definitely gonna push the boundaries of logic and physics a bit, huh?
Yeah, for sure. I mean, it makes you question what even counts as finishing something, right? We're working with some wild stuff here, philosophical analysis, and even the Stanford Encyclopedia of Philosophy.
Sounds like we're going deep.
Yep. Especially focusing on how supertasks mess with our ideas of mechanics and even relativity. So to kick things off, let's get a feel for just how weird infinity can be. Think you've got a handle on it.
Oh, I'm sure you're gonna challenge that.
Exactly. Let's talk about Hilbert's Hotel. Ever heard of it?
Rings a bell? Infinitely many rooms, right?
You got it. Every single room is full, packed with guests. But then a new guest shows up, needs a room. What do? The hotel's infinitely full.
Ah, but that's the trick with infinity, isn't it? You just shift everyone down one room. Guest one goes to two, guest two to three, and so on. Boom, room number one is free.
It's like a magic trick with numbers, right? But it shows how our regular ideas of full just break down when infinity's involved. And Hilbert Hotel is just the tip of the iceberg. Ready to tackle a real classic.
Hit me with it.
Let's talk about Zeno's paradox. You know, the one with Achilles in the finish line. He keeps running half the distance, then half of that distance, and so on forever.
Yeah, he never quite reaches the finish line, right? Because there's always another half to go, infinite halves.
Exactly. Seems like he's always approaching, but never actually there. But modern math has a slightly different take on it, doesn't it?
It does indeed. Enter the concept of a limit. We might think we can't add up an infinite number of things, but in math, sometimes an infinite series converges, meaning it adds up to a finite value.
So, like, even though it's infinite halves, they do add up to the whole distance.
Precisely. Achilles does technically reach that finish line in the world of math, but it does make you think about what complete even means, doesn't it?
Yeah, big time. There's no final step like in normal tasks. It's all about doing every single step in that infinite sequence, which is, well, a mind bender for sure. But you know what else is?
Oh, I remember you were about to tell me.
Let's switch gears to another famous one, Thomson's lamp. Picture this. A lamp being flipped on and off. On, off, on, off. But each flip takes half the time of the one before it. 2 minutes of this crazy switching, and then is it on or off?
Ah, this one's a real brain twister. Unlike Zeno's paradox, where those halves nicely converge, here there's no mathematical limit we can point to. You can't just look at the pattern and say, aha, it ends on, or nope, definitely off.
So is the whole thought experiment just busted? Meaningless?
Well, not necessarily. Some philosophers argue that the way we're deriving the lamp is just incomplete, like we're getting hung up on that infinite flipping, but maybe we're missing some key info.
Like how the switching mechanism actually works?
Bingo. Think about it like a bouncing ball hooked up to the lamp. If the ball completing a circuit turns the lamp on, it ends on. But if it breaking the circuit turns it off, well, you see where I'm going with this.
The setup matters, not just the infinite flipping.
Exactly. It's about looking at the whole system, not just the infinite part in isolation. And that, my friend, brings us to a whole other level of weirdness.
You're going to bring up jars and balls now, aren't you?
You know it, the Littlewood-Ross paradox. This one really forces us to face the music when it comes to infinity and discontinuity.
Okay, lay it on me. We've got a jar, right? But not just any jar. This one's got infinite capacity.
And then we've got infinitely many balls, all numbered.
All right, I'm picturing it. What's the task?
At each step, you add 10 balls, then take out one. Simple enough, right?
So far, so good.
But here's the kicker. You do this infinitely, many times, each step faster than the last. After this infinite flurry of adding and removing, how many balls are left in the jar?
Well, every single ball gets taken out at some point, right? Since we're doing infinite steps.
Logically, that seems sound. No ball is safe from being removed eventually, so 0 balls left.
But wait, hold on. At every point we stop and look, there are more balls being added than taken away. So shouldn't there be, like, infinitely many at the end?
And that is the heart of a paradox. See, with infinity, things get jumpy. We gotta choose. Either the ball positions are jumping around discontinuously from outside the jar back in.
Or the total number of balls in the jar suddenly plummets from tons to 0.
You got it. You can't have both be smooth and continuous when infinity is involved. Something's gotta give.
So even with something as simple as adding and removing balls, infinity throws a wrench in the works. It makes you wonder, can any of these supertasks actually exist in the real world? Or are they just like thought experiments for philosophers to debate over tea?
That's the million-dollar question, isn't it? And the answer might surprise you, because even classical physics, with its neat and tidy laws, might have some room for supertasks to sneak in.
Okay, now you've really got me intrigued. Classical physics and supertasks. Tell me more.
All right, picture this. We have an infinite line of particles, all spaced closer and closer together as you go down the line.
Okay, got it. Infinitely tiny particles, basically. What happens next?
Then we introduce another particle, this one's moving, and it smacks right into the first particle in the line. We're talking a perfectly elastic collision here, so all the momentum gets transferred down the line.
So like a chain reaction, but with infinite particles.
You got it. And the crazy part is, if you set up the distances and timings just right, this whole infinite chain reaction can happen in a finite amount of time, like, say, 1 second.
Wait, a whole infinite chain reaction in just 1 second? That doesn't seem possible. Wouldn't those particles have to move faster than the speed of light?
That's where it gets interesting. The overall speed of the system never actually goes above the initial speed of that first particle.
Huh. How does that work?
The magic is in those tiny distances. They keep getting smaller and smaller, so the time it takes for each collision to happen also shrinks. But there is a trade-off. To squeeze those particles closer and closer, their density has to increase. And not just a little bit, it has to increase infinitely, which is pretty wild when you think about it from a physics perspective.
No crazy speeds, but infinite density. That's a weird combo for sure. Didn't this same guy, Teres Larrañaga, come up with another super task with speeding up particles?
He did, yeah. This one involves an infinite line of particles, each moving towards the one in front of it. The catch is, each particle is moving twice as fast as the one behind it.
Okay, so we're ramping up the speed with each particle. Where does that lead?
Well, if you set things up just right, this one can also finish in a finite amount of time. But the result is even weirder.
Okay, now I have to know. What happens? Do they create a black hole or something?
Not quite a black hole, but they basically vanish from space.
Vanish like poof, gone.
Yep. Think about it. For any point in space you pick, there's a time before the supertask ends when a collision would have knocked a particle out of that spot.
So there's no place they could be at the end.
Exactly. It's called a space evader trajectory. The particles end up with no defined location.
Particles just disappearing into thin air. Doesn't that violate some fundamental laws of physics?
It does push some boundaries, for sure. This one actually needs those unbounded speeds we were talking about earlier, so it's not really compatible with Einstein's theory of relativity.
So not exactly real-world physics then.
Maybe not, but it's still a valuable thought experiment. It makes us think about the limits of classical mechanics, you know? What if we could push things to the extreme?
I like it. So we've got supertasks messing with classical mechanics, but what about relativity, where time itself gets all wobbly? Does that take it up even weirder possibilities for supertasks?
Oh, absolutely. Einstein's theory of relativity brings a whole new level of strangeness to the table. For example, imagine two people, Alice and Bob. They meet up at a specific point in space-time.
Okay, classic relativity setup.
Right. Now, Alice goes on a journey that takes a normal, finite amount of time. But Bob goes on a path that, thanks to the curvature of space-time, lets him experience an infinite amount of time.
Hold up, infinite time. Are we talking time travel now?
Not exactly time travel, but it does involve bending time in some pretty extreme ways. It's all about how the geometry of space-time can be warped. Some paths, while finite in terms of space, can correspond to infinite proper time for someone traveling along them.
So Alice is having a regular Tuesday, but Bob is off on an infinite odyssey through space-time. I'm still trying to wrap my head around that. What's the point of all this anyway?
Well, imagine Bob uses that infinite time to do some heavy-duty computing. Like, imagine he's checking every single number to see if Goldbach's conjecture is true.
Checking infinite numbers. That's a long computation.
It is. But if he finds a counterexample, he can send a signal back to Alice. And here's the kicker. Alice, after her normal finite journey, receives Bob's signal and instantly knows the answer to this massive infinite computation.
So Bob's like a superpowered computer crunching numbers for eternity, and Alice gets the cheat code to instant knowledge. But this whole Melamed-Hogarth space-time thing, it sounds pretty theoretical. Do these things actually exist?
That's the million-dollar question, isn't it? Physicists are still trying to figure out if these spacetimes are just mathematical curiosities or if they could actually exist in our universe. It's a real head-scratcher, isn't it? I mean, some physicists think one example could be anti-de Sitter spacetime.
Anti-de Sitter spacetime. That rings a bell. Did we touch on that earlier?
We did. It has a unique geometry that, get this, actually allows for those paths with infinite proper time. Someone traveling on one could experience, well, an infinite amount of time.
So that's how Bob could theoretically pull off that infinite computation, right? But wouldn't he be stuck out there, like, forever from our perspective?
Well, yeah, that's one of the catches. There's also the issue of those incredibly strong gravitational forces he'd experience on that path. Not to mention he'd need a lot of fuel, like an infinite amount, actually.
Yeah, infinite fuel costs are a bit outside most research budgets, I know. So any other options out there, maybe something a little easier on Bob?
There are, and they get even weirder. Imagine, for a moment, a cylindrical spacetime.
Okay, cylindrical, so shaped like a can, basically.
Yeah, you got it. Now, in this kind of spacetime, Bob could travel along a circular path, one that loops back on itself. This way, he experiences infinite time without needing any acceleration.
Ah, I see. So no infinite Joule costs and no crazy gravity crushing him. Sounds almost too good to be true. What's the catch this time?
Well, the catch is, this setup, it allows for time travel.
Time travel. Hold on. We were already dealing with infinity, and now we're throwing time travel into the mix. My brain hurts.
Yeah, time travel's kind of a headache. It really throws a wrench in things, messes with causality, and can lead to all sorts of paradoxes.
So it seems like even if we could find these Malamut-Hogarth spacetimes, using them for supertasks would come with a whole lot of baggage.
That's true. And there's also this idea from Roger Penrose, a pretty famous conjecture of his. He suggests that universes that make sense physically, ones that fit with our current understanding of physics, they shouldn't have those naked singularities that tend to pop up in Malamut-Hogarth spacetimes.
Naked singularities. Those sound a bit revealing.
They can be, but basically Penrose is suggesting there might be the fundamental reason why these spacetimes and the supertasks they might enable are just not possible in our universe.
So we're back to that pug of war again, huh? The tempting idea of infinite computation, butting heads with the limits of what's physically plausible, and, of course, the potential for all those mind-bending paradoxes we've been talking about.
Exactly. It's a fascinating area of research, and there's still so much we just don't know, but it really pulls us to think deeply about time, about computation, and about what's ultimately possible.
Well, we've covered a lot of ground today, from those ancient paradoxes like Zeno's to these mind-boggling ideas from modern physics, and it all comes back to this one wild concept, a supertask.
Supertasks are more than just curiosities. They're a really unique lens for examining some of the biggest questions in both philosophy and physics. They highlight the power of thought experiments to make us rethink what we thought we knew.
I mean, it's incredible to see how our intuition about what's possible, about how things work, can totally fall apart when you start to really grapple with infinity.
Right. And for you, our listener, someone who loves to delve into the philosophical side of things, I think supertasks offer an especially rich playground. They challenge us to go beyond our everyday understanding and confront the truly mind-bending implications of the infinite.
They show us that infinity isn't just some abstract idea mathematicians play around with. It's something that touches upon the deepest questions about the nature of reality.
Precisely. So as we wrap up our deep dive into supertasks, let me leave you with one final thought. What if we could build a Malamut-Hogarth machine, one that could send someone like Bob on that infinite journey? What computation would you entrust him with? What secrets of the universe would you want him to unlock?
And what would it mean for our understanding of infinity, of time, of knowledge itself, if we had access to such a powerful tool? It's a question worth pondering. And while supertasks might remain largely a mystery for now, their implications are vast, urging us to explore the outer limits of logic, physics, and the very fabric of reality. Until next time, keep those philosophical gears turning.